welcome to today's session, where we will begin exploring the fascinating world of machine learning with a focus on support vector machine algorithm, SVM algorithm. And I am delighted to introduce our instructor for the day, Mr. Pitamar Acharya, our distinguished research student at the University of Alabama at Birmingham. So let's welcome Mr. Acharya.
Thank you very much. So the topic of my talk is support vector machine. It is just the general introduction and the framework where the support vector machine lies. And the outline of my talk is it starts from the hyperplane, and then I'll go through the support vector machine, and then finally the importance of kernels. So in machine learning, generally we study two types of data, categorical data and quantitative data. So if you have label data, then the learning process is supervised learning. And if we have no label data, then that is unsupervised machine learning. So what do we want to predict in supervised learning? There might be categorical and quantitative variables. So if we have the categorical variables that belongs to the classification task, and if it is quantitative, then that belongs to regression. So in classification, there might be binary classification. So SVM is one of the classification tasks, although it is used in regression and outlier detection. Support vector machine is a kind of supervised method for binary classification. So it is the generalization of maximal margin classifier and support vector classifier. The maximal margin classifier is applicable to linearly separable data, and support vector classifier can be applied to the data which is not linearly separable, but the decision boundary is still linear. So before going to the support vector machine in detail, let me start with the hyperplane. So I'll go through the basic of a hyperplane. So in p-dimensional space, a hyperplane is a p minus one dimensional affine subspace. In two dimension, a hyperplane is a flat 1D surface. It is a line. In three dimension, it is a plane. So if we go beyond three dimension, then we call in general the plane is a hyperplane. If we have a 2D hyperplane, then we denote the equation of a hyperplane by this equation, b0 plus b1 x1 plus b2 x2 equals 0, where this is b0, b1, b2 are the constant, and we define here a point x. Let me say that this is two-dimensional, so we have two components. We have two components, x1 and x2. So if we have two components, then we define the plane by this relation. This relation is known as the hyperplane in two dimension. So if we have p dimension, then hyperplane is defined by p variables, x1, x2 up to xp. Then this relation will be the hyperplane in p dimension. If I replace this p0 by b and b1, b2, bp by w1, w2, and wp. So if I write this in vector notation, I use here the bold letter w, and x is the input vector. This is x is in component form, x1, x2. It is a column vector, and b is a bias term. Bias is sometimes we have the some kind of noise, and uh, so this is a scalar quantity. So hyperplane, if I write this as in a vector notation, this will be the dot product w dot x, or we can write this in terms of matrix multiplication w transpose x. So this is a scalar quantity, and we add here b, which is a scalar that equals to 0. So from here onwards, we use this notation to represent the hyperplane. So in case of a linear decision boundary, we have a number of criteria for training linear decision boundary. The first is the Gaussian class conditional distribution. And we also have the perceptron algorithm, logistic regression, and Fisher discriminant analysis. So, in detail, we are not going through all the decision boundaries, but a linear decision boundary is characterized by the direction. So, we have a normal vector W that will represent the direction, and bias is represented by B. So, in case of binary classification, we have a two class. So, we have to classify two data which can be represented by positive and negative data. So I represent here as positive one and negative one. Positive one when this hyperplane is greater than or equal to zero, and the negative classification for this hyperplane less than or equal to zero. So it consists of not only the plane, the region below that plane, and W cap equals one that represent a region above the plane. So we can think of hyperplane as dividing the p-dimensional space into two halves. Yeah, let's see here. We have two types of data. So let me separate this by class one and class two. So we can separate this by a linear. In two dimensional, it will be a line. So in three dimension, it will be a plane. And in if we have n dimension or p dimension, then we will represent this by a hyperplane. So the key assumption here is the classes can be separated by a linear distance boundary, and that can be separated by a hyperplane in case of binary classification. So let's go to support vector machine. So the hyperplane plays a great role in support vector machine. So let me go through the mathematical foundation for support vector machine. Suppose I have a classification type. So one type of data are this represented by circles, and those are represented by the rectangles, and they are separated by these three parallel lines. And those data which crosses the lines, they are known as the support vector, because these two data, or this we have three data, the two red ones and one the green circular data that touches those lines. So these three data play the important role. So we can neglect other, the remaining one. So this data represents the most important part of the topic. So these are known as the support vector because they support in determining the things that we want to study. So only the support vector decide the decision boundary in the support vector machine. So going further, I want to go in detail, but before that, let me revise the dot product. We define the dot product is uh, the scalar quantity if we multiply two vectors, and it is given by the magnitude of A, magnitude of B, and cosine of the angle between those two vectors. So in terms of projection, if I have B vector in this direction and A vector in this direction, then this this component or this distance will be the projection of this vector B in the direction of A. So the dot product, or simply I can write this in terms of transpose, it is defined as the magnitude of any one vector and the multiplication of that magnitude with the projection of other vector in the direction of the previous one. So in simply that is defined as the magnitude of A, magnitude of B times cosine theta, because I want to go through the projection. So here, let's sort of construct a normal vector W. If let's, I'm considering the two-dimensional here, and this is a W normal vector starting from the origin, and I construct three parallel lines. The center one is the hyperplane, and the surrounding two lines S1 and S2. This can be considered as a street, and the A's of the streets are the gutter. We call this gutter S1 and S2, and S0 is the hyperplane. So all the points in the hyperplane have the same projection in the direction of W. This gray line represents the points in the hyperplane. So this vector, if they projected here, the green line represents the projection. The projection is always the constant here. It is the scalar product divided by the magnitude of W. That will give the constant because the projection distance is always the constant. I'm taking the dot product here. So, and then multiply by the magnitude of W on both sides. So we'll get this quantity. And if this C times W is some kind of scalar, and fixing this, I substitute this as negative B. So I'll have the plane W transpose X plus B equals 0. This is nothing, just the hyperplane equation. And I separate the data. For example, I have the negative data on the lower side and positive data on the upper side of the hyperplane. So they are separated by the gutter S1 and gutter S2. This is the hyperplane. Hyperplane is W transpose X plus B equals 0. And the upper one is W transpose X plus B equals K. K is some constant. And W transpose X plus B equals negative K. And the lower region is represented by W transpose X plus B less than 0. And the upper part is represented by W transpose of X plus B is positive. Here, I replace the constant K by 1 so that the gutter S1 will become W transpose X plus B equals 1, and the lower gutter S2 will become W transpose X plus B equals negative 1. Still, the reason is W transpose X plus B is less than 0. This is the reason for a negative data, and the positive data are represented in the region omega transpose X plus B, which is positive. So the support vector machine here, the main target is how to maximize the width of the street. So before maximizing the width, we have to determine what is the width of this street, because we are considering this street because the support vectors are, there are four data. This is the negative data on the lower side. These two are support vectors here. And the position vector are represented by x minus. I'm representing the negative data by x minus. This is the position vector. And the positive data are represented by x plus. So if I use the vector addition rule, the width of this street is given by x plus minus x minus. This is the width of the street in vector notation. So the upper side can be represented by omega transpose x plus equals 1 minus b, and the lower part is represented by omega transpose x equals negative 1 minus b. So these are the representation for the two data points. So if I want to find this in terms of the width in terms of a scalar, I have to multiply this by a unit vector. The unit vector here in the direction of W is given by W vector divided by the magnitude of W. So if I manipulate this, I will get the value 2 over magnitude of W. So that gives the width of the street. So our job is to maximize the width of the street. If we maximize the width of the street, we have great place to separate the data, and the accuracy might be. So in order to optimize the width of the street, we have the optimization function here is 2 over omega. Here, maximizing 2 over omega is not a good idea. So this is equivalent to maximizing 1 over omega, which is equivalent to minimizing of omega, magnitude of omega. So I replace this minimizing of omega by minimizing half omega square. So I have used this particular quantity because this is mathematically convenient to optimize. Now the objective function will be this 1/2 the magnitude of W square. Subject to, we have the constraint here. So we have two regions, the scalar product W dot X plus B, or W transpose X plus B greater than 1, and another region we have less than or 1. So if I take the y, the two classification, we are taking y equals positive and negative 1. So this will be the constraint. So our job is to use the Lagrange multiplier to optimize the function. So if I use the Lagrange multiplier and construct a Lagrangian function is half of magnitude of w square minus alpha I times this particular quantity that is taken from the constraint. So here alpha I represents the constraint multiplier, and I'm taking the sum over all the constraint. So if I take the partial derivative of L with respect to W, that is the uh, normal vector, then the value of this normal vector W, we can consider this as the weight, and this will be the decision vector in a linear sum of the samples. So if we optimize this, taking the derivative of L with respect to W, then the value of W will be this one. So if we take the derivative, partial derivative of Lagrangian function L with respect to the parameter B is a bias here, then the value here is alpha I times y equals 0. So resubstituting these all values in the Lagrangian function, then the ultimate Lagrangian function will be L equals the sum of alpha I minus half and the double sum of I and j, alpha j, yj, and again the scalar product of two quantities, xi and xj. So here, optimizing this value and finding the value of w will give the maximum margin. Here comes kernel. So that's all about the linear boundary. But the many real world data set cannot be separated by using linear detects, linear decision boundary. For example, the data are complicated. So if you want to find the face recognition, the linear decision boundary may not work. So how can we apply a linear classifier to the data that is not linearly separable? So here we transform the data by preprocessing and generate nonlinear features. So nonlinear features plays an important role if we have the complicated data like facial recognition. Here, this is not possible if we have a linear boundary because we have the data here, positive data, negative data, positive data, negative data. So we cannot separate the data. So in this condition, we can transform by a function phi. We have an input space x, and we transform the space variable x into another multidimensional feature space represented by phi x. This is a feature space. This is a one dimension and this is a two dimension. So we can separate this in terms of uh, like a parabola. So here we can see easily that the positive and negative data are classified by a linear boundary. So what if this phi x is really big? Then kernel is the answer. The objective is to find a kernel key such that kernel of two vector x and x prime is the scalar product of the two quantities in the feature space. If we take the scalar product and denoted that by k, which is the kernel, then that value, the computation of that value will be faster, and we can use the kernel directly in support vector machine algorithm rather than the scalar product in the simple space. So this approach is possible. So people define the kernel trick as the kernel can be used to determine uh, the matrix. So matrix can be defined as positive definite. If we have a matrix A, then X transpose AX If it is greater than zero, or greater than or equal to zero, then we can say that's a positive definite. So in terms of positive definite, we can define a kernel tree. But the simple formulation here is given an algorithm which is formulated in terms of positive definite kernel. This is simply a matrix, and this uh, positive definite is simply this is greater than or equal to zero. And we can construct an alternative algorithm by replacing the kernel K1 with another positive definite kernel K2. So support vector machine use this idea of kernel, it is used to classify the data either linearly or non-linearly. There are many types of kernel, but the particular importance kernel are a linear kernel. It is simply the uh, scalar product of two vectors. So that represents the dot product, which is used in visual pattern recognition. Similarly, but a little bit complicated, with the degree P is a polynomial kernel. It is 1 plus x transpose x prime to the power P. Another is the sigmoid kernel. It is tangent of hyperbolic function. It is used in activation function in neural networks. And a supportive vector machine with signal kernel is equivalent to a two-layer perceptron. Similarly, we have the cosine similarity kernel, which is popular for measuring similarity between text documents. And the most popular is the radial bias function, which is a widely used kernel for nonlinear support vector machine. Here, gamma is the constant in exponential of negative gamma, and the norm of x minus x prime square. That gamma is similar to the Gaussian distribution in probability function, which is taken to be 1 over sigma square. So sometimes we multiply by 1/2. That means gamma is equal to 1 over 2 times sigma square. If this is a
I
radial
have,
basis function, so, yeah, do you have any questions?
I have a question on the kernel.
Okay.
Kernel says that the linear kernel it transforms the two-dimensional data into single dimension. I think every kernel shows that one. When you show this is an example previous slides, we can transform the one-dimensional to multi-dimension.
In case of linear kernel?
Yeah, the like linear and linear kernel. The inputs are there are two inputs, right?
Yeah, input, but the
X and
output is the single, yeah. Because it is the
single. That
scalar
means we are
product.
transforming two-dimensional data into single dimension.
Yeah, because that is the scalar product. That is simply a
Yeah,
real
right.
number.
And what about the other one, like uh, sigmoid? Is
Yeah,
that the same?
sigmoid, because in case of sigmoid, if you see the graph of sigmoid function, you can treat this as some, it is the combination of exponential function.
Mm-hmm.
And yeah, and this BF is the tangent of hyperbolic function, and the limit will be from -1 to +1. So, that can be further reduced into rectilinear rectified unit ReLU, and that can be further treated as a probability function, because most of the things that are not deterministic can be calculated or predicted by the probability. So we can yeah, use this as a probability function. All right.
Okay. Okay. Thank
Thank you. Yeah, I have generated the code here for this one. Well, let me go through. Here in Google Colab, I have, yeah, this is the example. Mm, yeah, I have the data set of email, that's 4601 emails, which are spam or not spam. So I pick up 75% of the data is the training data, and other 25% is the testing data. So we can find the accuracy here. Uh, yeah, these are the features. We split the data into features and labels. We represent 1 for spam and 0 for not spam. The testing and training data set are here with the random state 42. and then we scaled the training and testing data. So the SVM results will be, yeah, we can see that the linear kernel accuracy is 0.9288. The polynomial kernel accuracy is 0.83. And from in case of RBF kernel, Gaussian kernel, the accuracy is 0.9366. So this is the most popular because we can get the greater accuracy. So if I compare this with some kind of random forest classifier, it resembles the same. So accuracy here is also with 0.9583. So that plot I generate here by taking some random data. Yeah, this is the nonlinear classification by using support vector machine here. And the kernel here is the Gaussian kernel. Let me go back to the slide. So what are the properties of support vector machine? Yeah, it has greater flexibility with kernel function. Support vector machine allow the use of various kernel function, and they are useful in handling nonlinear relationship in the data. And only the support vectors are used to define the separating hyperplane, so it is efficient in case of large data set. Also, in case of high dimensional feature space, they are effective when the number of dimension exceeds the number of samples. In case of supervised learning application, support vector machine are used not only for classification types, they are used for regression and outlier detection. But outlier detection is also possible, but most of the case it is used in binary classification. Yeah, the mathematical property is fascinating. So people use the simple convex optimization problem, they use Lagrangian function to optimize it, and the convergence to a unique global solution is guaranteed. So there are a lot of application of support vector machine. So in case of inverse geosounding problem, that means if we want to understand the internal structure of the Earth, so by studying the surface of the Earth, you can determine the subsurface Earth structure that is used in seismic wave propagation. In case of um, earthquake study, people generally use inverse geosounding problem. The kernel method of support vector machine plays a great role in solving those problems. Also, support vector machine based modeling of seismic liquefaction potential. This is also based on earthquake. So sometimes when there is an earthquake, then the pressure is high in case of water. So there will be the less friction in the soil. That means that soil will be as a liquid. So so in this case, in modeling the seismic potential, support vector machines are useful. Also, in case of um, great research in protein folding, the three-dimensional protein structure is important to study the human um, biochemistry. And in case of mathematical biology and in medical sciences, uh, the support vector machine can be used to determine the 3D structure of protein folding. Yeah, I already said in case of facial expression classification in high dimensional data, it is useful. In depth and discharge prediction in semicircular and circular shaped channel, like in hydropower irrigation, it plays a great role. Also in texture classification, the support vector machine are useful. For example, of image might be smooth or rough. How can we classify the data? Support vector machine plays the great role. And there are personal recommendation system for news website. There is a support vector machine driven news website called EWS Rec. And support vector classifier are also useful in lane cover classification. Many ecologists and environmental scientists use support vector machine to the lane cover classifications, like the soil part, the water part in the earth, the fertile land, the barren land. So that classifier will be the support vector machine. So by there is a demo of support vector classification by Woody Aroni. So let's see this visualization. Here, blue and red dots are binary data, and we use a polynomial kernel. So this is a simple two-dimensional space. Now we project this into multi-dimensional. It's like a paraboloid, and that's a hyperplane. Now the hyperplane can separate two level of data, two classification data, and binary data easily.